we have some fantastic guests along the way. Just if you're interested, I've been at Microsoft now for 30 years. I've always been involved in security in one way, shape, or form. One of the folks behind the security development lifecycle back in the day, the SDL. Also was the application security lead on the Rio 2016 games that ran on Azure back in the day. Also written a few books along the way. The latest book just came out in December last year, which I did with a couple of colleagues of mine, Simona Kurtzi and Heinrich Gantenbein. A lot of fun writing that book, and really sort of coalesces a lot of our practical thoughts around what it takes to design and develop cloud-based solutions on Azure. Now, I really want to level set before I sort of get stuck into this. It's sort of an ongoing joke within the team that I'm sort of the resident security nerd amongst a whole bunch of database engineers. I went to Midjourney and said, "Hey, give me a picture of what that might look like," and apparently that's me in the middle. Also, you got to say no beards. Apparently, if you say database engineers, it gives them all a beard. So I don't know what to say about that. So anyway, I turned off beards, but apparently that's me in the middle in a hoodie. In fact, the only hoodie I actually have is actually a SQL Server 2022 hoodie. All right, so what are you going to learn in this? So first of all, just some of the core elements of secure design, like what it means to design secure systems. And then we'll look at some of the appropriate, the technology that we have in Azure SQL Database and SQL Server 2022, and how you can sort of apply them when it comes to designing a secure system. I'm a big believer in understanding security. I don't mean you have to be a security alpha geek. In fact, that's the last thing I want. The last thing I want is for everyone to be a security alpha geek, because if you were a security alpha geek, we would never ship a product ever again, because everyone would have some security gripe, that they didn't like. But you really do kind of have to understand, why you're choosing the technology you're choosing to mitigate specific threats. This is really important. You've got to understand what you're really mitigating. Like it's all very well just saying, hey, we're going to use an ABC or an XYZ or a 1, 2, 3 or whatever. But what are you actually mitigating? Because if you don't understand that, you're literally just throwing security technology at the wall and just hoping that it will stick. And you can't design systems like that. You've really got to understand what threats you're actually mitigating. So before we sort of get stuck into the main content, I really want to add a little bit of structure. In fact, this is actually lifted directly from the book. This is actually from the database chapter, which is chapter 13. And when you're thinking about security technologies that you have at your disposal, it really falls into these categories on the left-hand side there: authentication, authorization, audit, and then there's sort of the 3 buckets of crypto at rest, on the wire, then in use. And in use is actually a relatively new thing, especially when you talk about confidential computing. And then finally, network isolation. That's obviously a big deal when we're working on the Azure backend, right? Is isolation of the environment. But then there's also 2 distinct ways of looking at these mitigations. There are those mitigations that affect the control plane, which is sort of the management of the environment. But what I mean by that is like admins, customers who are administering the environment, and then the data plane, which is users using the system, and they have different mitigations. I mean, obviously some of them are in common. I mean, obviously, but you got to think about when to enable, again, ABC. Well, is that which of these security properties does that address, and is it a control plane control or is it a data plane control? And you really have to think about both of them. So sort of a bit more fleshed out. If I take this as a starting point and flesh it out a little bit more with security services in the SQL Server family, so that includes Azure SQL Database, SQL Server, SQL MI, for example, or SQL Server in a VM. It's those sort of the family of products and the different technologies that we have at our disposal. I'm not going to go through all of these because during the presentation I'll sort of touch on some of them. So this is like authentication, authorization, audit, crypto on the crypto at rest, and then control plane, data plane, and then finally you've got crypto on the wire, crypto in use, and network isolation. Again, control plane and data plane. So let's go through some of these in a bit more detail. So the first one I want to look at is authentication at the control plane and the data plane. The important point about, actually, let me back up a minute. Whenever I ask people, hey, what does TLS do? They always say the same thing, or variations of it. It protects my credit card information on as it flies around the internet, which is true. But that's secondary. Don't get me wrong. I'm not saying it's not important, but it's secondary to server authentication. The single most important security service that TLS provides is server authentication. You can't have a secure channel until you've authenticated the server. You cannot, because you don't know who you're talking to. So what's the point? The analogy I like to sort of use, and I hate analogies, but the analogy I like to use is like whispering a secret to somebody in a blacked out room, but you don't know who's in the room. So when I see people, being really lazy and like rolling out like self-signed certificates, and heaven only knows what else, and that is not good TLS hygiene, because you do not know who you're talking to. So correct TLS configuration is absolutely critical. Look, I wouldn't mind if configuring TLS was hard, but it really isn't. I mean, don't get me wrong. I mean, SQL Server 22, the few little bells and knobs and buttons you got to press, but once it's working, it's working, and it scales really well. It's fast once it's going. It's really important that we do TLS correctly, because that server authentication step is so important. I hear people say, well, we use self-signed certificates in dev, and then we use real certificates in prod. The answer is no, you should be using real certificates throughout, because if you're using self-signed certificates in dev, you're not testing the same environment, or even you're not using the same environment as you are in production. Right? Because you're not, I know full well that if you're using self-signed certificates, you're not doing all the correct certificate checks. You're not, by definition, you're not. So it means you're not testing it correctly. You don't even know if it's going to roll out and run correctly. You don't know. So that's why you should just use, proper certs in development. Now, does that mean you need to go out to these, well-respected and well-known CAs, certificate authorities, and buy their certificates? Not necessarily. You could actually you could actually have your own Microsoft certificate services running in a VM and have it issue certificates. So at least you've still got a hierarchy of certificates and root certificates and so on. And then all you need to do is make sure that all the development environments have the dev root certificate installed on their box. At least I know you're doing all the correct checks, right? All the correct certificate checks. And you could actually have a certificate that, that mimics quite closely to what the certificate looks like that comes from a CA. But please just don't go doing self-signed certificates. Look, I know full well that SQL Server makes it easy to use self-signed certificates, but just don't. We should be just doing that. It's not like we don't know how to solve this problem. We actually do. So just don't, right? Just use TLS correctly, use certificates correctly. And if you must have your own internal CA, that's what I do, then so be it. But don't use self-signed certificates. I'll get off my soapbox now. Don't worry, I'm going to get back on another soapbox in a minute. So in connection strings, there's really a couple of options you need to worry about. The first one is encrypt equals true and trust certificate, service certificate equals false. These are the settings that you should have. I actually don't like the term encrypt, because it's more than encryption. It's really sort of channel protection. But encryption is obviously one of the services that's provided by TLS. But really that means encryption and tamper detection, because both are provided by TLS. And the next one is really important. That's trust server certificate. If you have trust server certificate equals true, that means connect to absolutely anybody. I don't care who it is, because I'm not going to validate the server anyway. I mean, you could be connecting to anything. And by saying trust server certificate equals true, you're basically saying, look, I'll happily connect to absolutely anybody. And I'm sure that's not what you intend. And so that's why you should always have trust server certificate equals false. What that means is do all the appropriate certificate validation. That's what it really, really means. So in SQL Server 2022, there's a new option called encrypt equals strict, which basically disables trust server certificate. That's important. What that means is it's going to do all the appropriate checks against the certificate, to make sure the certificate is correct automatically. It also allows the use of TDS 8. So tabular data stream version 8 is now available in SQL Server 2022. And one of the biggest things that we did is we broke apart TDS and TLS. For those of you not aware, historically, TLS and TDS were sort of interleaved between each other, which made it very, very difficult to actually upgrade, say, TLS outside of upgrading TDS at the same time. But now we've broken those two apart, which is nice. That means that we can evolve over to newer versions of TLS without upgrading TDS. It also means that we can terminate TDS connections over TLS at, say, a firewall, and do packet inspection, or on egress and do packet inspection, so for data loss protection prevention. So this is really nice to see. A lot of engineering went into that to make sure that that works. All right, so that's server authentication out of the way. Basically, the correct answer is TLS. Everything else is wrong, and you should be using anything but self-signed certificates. So, if you don't understand how certificates work, I would definitely recommend that someone in your team or in your company understands, and perhaps you set up your own test or development CA, so you can actually experiment with real certificates and do real certificate validation. So now let's move our attention to client authentication. So basically the correct answer here for most environments is to use Azure Active Directory. And there's some really good reasons for that, which I'll come on to in a minute. So AAD is the identity provider for Azure, as I'm sure you're all very well aware, and it issues OAuth 2 authorization tokens after the user has been authenticated. It's always preferred for client authentication for a number of reasons, but one of the big ones from a sort of pure security perspective is that AAD handles the credential. There is no credential. There is no storing of a password anywhere on the box. It's all handled by AAD. The credential is not there. There's no credential verifier maintained by SQL either, right? There's nothing there. So it means that in the case of like zero trust assume breach, it's for less, assume breach basically means, okay, the environment's utterly destroyed. Now what? In this example, the now what is, well, the attacker has nothing. There's nothing there. Which is fantastic, right? So I always find that of the three pillars of zero trust, assume breach is the one that sort of clears the head very quickly, because you're asking the question, okay, the environment is now completely destroyed. Now what? The attackers have complete and unfettered access to the environment. Now what? In this example, the attacker does not have access to anything that even represents the credential or can verify the credential. It's just not there. For non-user accounts in Azure, the managed identities are always preferred because, again, it's the same thing. The credential is handled by AAD. Really, really important. So you can assign a managed identity to say, a VM or say an Azure function app. You can even do it to Azure SQL database as well, and I'll give you an example of how that works in a minute. But this is really important because, again, the credential is not, like, let's say you have a VM, right? Let's say you assign a managed identity to it, either system or user, it doesn't really matter. And the VM starts up, and then connections are made out of the VMs. Let's say you got a C# application running in there. You can make the C# application connect under the identity of the VM. Just a little simple change, not rocket science. But again, there's no credential being stored anywhere, which is incredibly important. So if the VM is compromised, there is no credential that the attacker can get hold of because it's all handled by AAD. So I talked before about SQL auditing. So you can turn on SQL auditing, and if you haven't, please do so. The number of people actually doing SQL auditing is abysmally low. We really want people to use it because it's really good in the case of when things go bad. You'll notice here there's actually two options, right? For authenticating to the storage account. You can use multiple ways of storing the audit log, but storage account is very, very common. But you need to authenticate SQL Server to the storage account. And there's two ways of doing it. One is to use a managed identity, and the other one is to use a storage access key. Managed identity should be the preferred option. What will happen when you click on this, we will automatically, if one doesn't already exist, provide a managed identity for that running instance of Azure SQL database. And then we'll authenticate that to the storage account and then provide authorization checks using that particular identity. Now, if you had a storage access key, the first question I'm going to ask if I'm reviewing your threat model or you're looking at your design is, where are those keys stored and how are they protected? And that's so important that you understand how, ultimately how these things are protected. And again, that's why I prefer managed identities, because AAD handles absolutely everything. There's nothing for you as a developer or an architect to store. There's no need to do that whatsoever. So let's go and look at our design super duper fast. I'm not going to spend much time on this, but here's our SQL instance in the middle. Here's our user using the system. We're using TLS absolutely everywhere. We've got OAuth tokens flying everywhere. And we've got our log files being stored over here in a storage account. And we're going to build on this as we move through it. So next thing at the control plane, we have authorization. So how do we do that? Well, in the case of Azure, it's all RBAC, right? Role-based access control. And basically what you would do is you would assign specific user accounts, a sort of membership to a role. So for example, you could have like a SQL database contributor who can do databasey things, but they can't change security settings and they don't have access to the data because it's a control plane policy. It's not a data plane policy. So you don't have access to the data. And then a security manager, another example, right, where you can manipulate security settings, but you can't, again, view the data, and you can't sort of delete a database. Now, if you look at how it's actually defined, if you look at, say, the SQL Server contributor role, this is actually kind of interesting. And in fact, this is often a light bulb moment for a lot of people if they've never actually seen the JSON representation of a role. So again, here's the role for SQL Server contributor. You see, you got actions, not actions, data actions, not data actions. All these here that are under actions and not actions are control plane. Everything under that is data plane. As you can see here, for SQL Server contributor, there are no data plane actions. There's no data plane RBAC at all. You don't have access to anything at the data plane, but you can, delete a SQL Server, well, SQL instance, or change the scaling on one, the underlying infrastructure of it. That means basically you can do anything to SQL databases. That star means anything, but you can't read the data. So hopefully this is, if you're not familiar with what the representation is of a role, this is just one example. Hopefully it makes a lot of sense. And you can see here that this is actually a control plane role and not a data plane role because it has no data plane actions. Now let's look at authorization at the control plane and the data plane, but for SQL. Now SQL's kind of funky, right? Because it's got its own database permissions and roles that have been around for a long time, and people know, and some people know and love them, but we're familiar with them, right? And so there's a whole bunch of them available at the server level, at database level. My colleague Andreas Walter is doing a lot of work here around trying to provide more granular permissions. So there are some permissions or some roles that have a lot of ability, and some customers say, well, we don't want, let's say it has 5 capabilities just to come up with a number. Some customers say, well, we don't want to grant all 5. We want to grant someone just the ability to do the one thing. And so that's why Andreas is working in this area a great deal on trying to break up some of those permissions to make them a bit more granular. Next is now sort of wandering into the territory where I tend to get really bogged down in details. So I'm going to try and mitigate that a little bit. For crypto at rest, these are the cryptographic controls. So the first one I'm going to look at is cryptography at rest. By far the most well-known is transparent data encryption, which I'll talk about really quickly. But before we get on to that, I want to explain something about cryptographic controls. You may have heard this whole adage of, security is only as good as the weakest link. It's not true. It's just not true. There is a reason why some of these controls are often referred to as compensating controls. They're there to compensate for failure in other controls. So for example, you could have a system that's got like a firewall, you're running at least priv, you have anti-malware, you do this, you do that, you have strong authentication, strong authorization, blah, 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 right? The whole 9 yards. But for some reason, the attacker manages to get in anyway. They get blow the firewall away, manage to get elevate privilege, become an admin on the box, bypass all your RBAC policy, and now I'm reading the data. Well, it's encrypted with strong key policies. Oops, right? The attacker just gets ciphertext back. They don't get plain text. I mean, does it suck? I mean, yeah, it sucks, right? But it sucks less than getting the plain text back. So cryptographic controls are an unbelievably valuable last line of defense, and they should be really taken seriously with good key management and good design, obviously. The first one, which we all know of, I guess, is transparent data encryption. It's been around for a long time. It's very easy to use, 0 code changes. You just basically flip a switch. A bit more to it than that, but basically you flip a switch. It's designed to, and this is really important. Remember I said very early on, you need to understand what threats you are really mitigating with various controls. So transparent data encryption is designed to mitigate the disclosure of sensitive data from a stolen device, a stolen data volume, or even a stolen machine for that matter. If you've got a machine under your desktop and someone gets into your house and walks out with it, then TDE should mitigate that. What is really important here is also encrypts backups with the same keys. So, and they are kept well away from SQL. And so that's why to restore it, you got to bring the restore into a database that has the same access to the same keys, and then you can restore it. the root key, it's actually a key hierarchy. The root key, which is an RSA key, should be stored in Key Vault. That includes SQL Server and a VM. We can do that as well. But it is there to provide encryption only. So some of the new TDE features, some of these are actually new. I think the top 2 are new, I think, and the bottom 2 are in preview. Could be wrong there, but anyway, they're certainly available to kick the tires if nothing else. First one is automatic key rotation of the TDE protector key, which is the root key in Key Vault. That's actually a Key Vault feature. You can do the same thing with storage accounts today as well, where we will automatically rotate that on, say, I don't know, 6-month basis, 12-month basis, whatever is appropriate for your compliance requirements. Also, user-assigned managed identities for TDE using a customer managed key. Historically, that was only a system managed identity. And we also have now per database transparent data encryption keys and multi-tenant TDE keys. It's actually interesting. They're both kind of at opposite ends of the spectrum. Per database key, historically, keys were always at a per server level. So now you can do it per database, which is interesting if you've got like a single server handling, let's just say, make it up, say legal and HR. You can now isolate them, not just through permissions, but also cryptographically too. And then multi-tenant TDE key is where you can have a set of keys that span across multiple tenants. Some customers require that. All right, so that's kind of TDE out of the way. So let's talk about the next one, which is one of my favorite topics, which is always encrypted. So I sort of mentioned before that there's a spectrum of stuff. Well, here's a really good example of a spectrum. Just getting philosophical for a moment. Databases are designed to be queried, right? That's the whole reason why they exist. I mean, sure, you can insert, you can delete, you can update, etc. But querying is a big part of databases. I'm sure we all agree on that. Then at the other end, you've got cryptographic control, or more importantly, encryption, is designed to prevent querying. So you've got these things that are totally at odds with each other. These engines are designed to be queried, but crypto, which we require, or encryption, I should say, we require, prevents it. So how do we meet in the middle somewhere? And that's where Always Encrypted comes in. Now, for anyone who knows some of my work, you'll know that I'm really, really pedantic with my words, especially when it comes to cryptographic controls. In fact, I think I drive people nuts when I'm sort of saying, okay, precisely what do you mean by that sentence? I'll hear people say, well, we need to protect the certificate. It's like, nah, you don't need to protect the certificate at all. Certificates are public information and they're self-protecting because they're digitally signed and they contain nothing sensitive. So you don't need to protect a certificate. I care about protecting the private key that's associated with the certificate, but not the certificate. Certificate can be on the internet, doesn't matter. So this next sentence, I'm going to read verbatim and sort of explain it a little bit as I go through it. Always Encrypted allows you to perform some queries over encrypted data without decrypting the data at the server. Each one of those core points is really important. Performs some queries, not everything, and it doesn't. You can do inserts as well and updates and so on. Obviously, it's not just queries, but it can perform some queries, not everything, over encrypted data without decrypting it at the server. Really, really important point there. And again, we'll come on to that as I explain kind of how it works. So with Always Encrypted, there's 2 flavors of Always Encrypted. There's with and without enclaves. The without enclaves version is available in SQL Server, on-prem, in a VM, as a SQL database, MI, and even in Cosmos DB. And with enclaves, there's 2 flavors of that. I'll touch on each of these momentarily, but there's SGX enclaves and VBS enclaves. And the VBS enclaves for Azure SQL database is actually in preview right now. Again, I'll talk about these in a couple of slides. This is the most important point. In all scenarios, if you're using Always Encrypted in either flavor, enclave or non-enclave, the encryption keys are not in server memory. They're not in SQL Server's memory. They're not there at all. And you may have already gathered by now that I'm a big fan of zero trust, assume breach. So what's important there is that if the server is compromised, the keys are not there. They're not there at all. So the attacker can't get the decryption keys. Now compare and contrast that with column encryption, which has been around for a long time. By the way, column encryption is not always encrypted, but column encryption has been around for a long time in SQL. and the keys for doing encryption and decryption are in memory. So if the attacker could start, looking through SQL Server's memory, which attackers can often do, the attacker can get the keys, which is probably not a good thing. Now, for Always Encrypted, I'm going to be absolutely honest with you. May as well pull the Band-Aid off here. The odds are really good that if you have an existing code, you'll need to make pretty serious code changes to get it to work with Always Encrypted. However, if you're designing, sort of a greenfield application, then you should really plan for it from the get-go, like which columns and which tables we're going to, encrypt using Always Encrypted, and then what do our queries look like? And sometimes you may need to denormalize some of the data to make it work, efficiently, or correctly. So you need to think about that sort of stuff. Now, even though I didn't really say this, I said the keys aren't in the SQL Server server's memory, which is true. The client does have to have access to the keys, right? So if you've got 100 clients or something, they need to have access to the keys, and they can be stored in Key Vault, or they can even be stored using the in the certificate store in Windows as well. Key Vault's probably the easiest, to be honest with you. Now, what happens is that in the case of the Enclave version, we will actually do some of the queries in this special thing called an enclave. Now, an enclave is a cordoned off piece of memory. Now, in the case of SGX enclaves, which is Intel Software Guard extensions, the delineation between who has access to that region of memory and who doesn't is determined all the way down to the CPU. Right. So the decision is actually literally the decision is made by the CPU. If you compromise SQL Server and you say, okay, let me go and look for the code that is the SGX enclave, you won't see it. It's not there, because the Intel CPU won't let you look at it. The other one is virtualization-based security, which is available in preview right now for Azure SQL Database. It uses the hypervisor, that we have that we use to isolate one VM from another. That's the exact same technology that we're using, but we're using it to have this little enclave of memory. Now, in the enclave, we basically load a small portion of the SQL query engine. The actual code that actually does the query is loaded into the enclave, and it will actually decrypt data. And I'll show you a little picture of this in a moment. But if you want to really have something that's rich and secure, then enclaves are the way to go. So as I mentioned before, we have two versions of the enclaves. We have SGX enclaves, and we have VBS enclaves. As you can imagine, because the SGX enclaves, the decision, the go, no go, like who has access to the enclave and who doesn't, that is all the way down in the CPU, which means you must use a specific kind of CPU. So when you're provisioning your hardware, you must opt in for the compute that actually handles that actually has these built-in CPUs. These are a special DC series of hardware. The downside today is that both region and compute size is limited today. That's eventually that will change, but just be aware of that. There is a limitation there today. With VBS enclaves, which is currently in preview for Azure SQL Database, there are no hardware dependencies, and basically every region supports it. The more sort of strict isolation mechanism is SGX, however, but VBS is still a fantastic isolation technology. Now, just to confuse things a little bit more, there are two major ways of encrypting a column. Actually, technically, you could say three ways. One is no encryption, which doesn't really count, but then the other two are deterministic and randomized. If you're using no enclaves, you must use deterministic if you're doing a query over that column. And you're limited to equality and inequality. That's all you can do, which may be fine for some customers, maybe fine for some kind of workloads. However, if you're using enclaves, you can actually use randomized encryption. And you can do things like, greater than, less than, those kinds of things, which you cannot do if you're using a non-enclave version of Always Encrypted. The non-enclave version of Always Encrypted is a lot simpler, because there's fewer moving parts. But you're also limited to the SQL statements. Well, is basically 2 equals and doesn't equal. I'll sort of give you an example, kind of how it works in a minute. So you got 2 flavors of Always Encrypted using using enclaves and not using enclaves. And for enclaves, you have 2 versions, VBS and SGX. And then when you're looking at a column, you can encrypt it using deterministic or randomized. And again, if you're using enclaves, you can use randomized in a lot more places than the non-enclave version. All right, so kind of how it works. I'm not going to go through all the gory detail here because it is kind of gory and detaily. So essentially, all the work is done by the client driver. By driver, I mean the ODBC driver, OLEDB, JDBC, whatever you're using, which most of in fact, all the current drivers support it. So essentially, it kind of works this way. Imagine you're inserting a row into a database, and it's been configured for Always Encrypted, and it doesn't matter if it's enclave or not. Let's say you do insert blah 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 table blah 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 values blah blah blah, and then a social security number. Let's just call it 1 2 3. I know it's bigger than that, but I need to save time. So you do insert into table blah 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 1 2 3. The client driver has already read the metadata from SQL Server and says, oh, that SSN column is actually encrypted using, let's just say, deterministic encryption. So what it will do is automatically, it will, in the driver, not in your code, in the driver, so let's just say the JDBC driver, it will automatically encrypt that cell. So 1 2 3 now becomes whatever it is in ciphertext. And then that will then go across the wire, and then SQL Server or Azure SQL Database will just store it. Even though as ciphertext, nothing is decrypting it, nothing at all. It's being inserted into the database or into the table as ciphertext. Let's say you now do a select. Let's say you do a select star from table where SSN equals 1 2 3. That's in your driver. So the driver will say, oh, hang on a minute, that SSN column is encrypted. I need to get the key. So obviously it caches the key, by the way, just so you know. We're not going to keep fetching the key every 5 secanes. And you can put a timer actually on the how long the key lasts. But anyway, so it then encrypts 1 2 3. So it becomes, let's just say it becomes ABC. Obviously it's more complex than that, but and that's, let's say it's the ciphertext. So what the server sees, it then sends that query up to the server, and so the server sees select star from table where SSN equals ABC, which is the ciphertext. It will do a comparison against the 2 sets of ciphertext. And if they are the same, that's why deterministic is so important. If the ciphertexts are the same, it will return the row or rows back to the customer without decrypting anything. The client driver says, ooh, that column is encrypted. I need to decrypt it now. And so it will fetch the key or use the cached version of the key and decrypt that column or of those rows, and then give the plain text back to the user code. What's really cool is your application did no encryption and decryption whatsoever. It was all done by the driver. The SQL Server did none either. So it's all being done by your driver, which is really, really nice. Very efficient, very, very fast. And in the overall scheme of things, very elegant as well, because ultimately all you're doing is you're comparing ciphertexts. But you can't do you can't do greater than with this, because if you do where social security number is greater than 1 2 3, you can't really predict what the ciphertext is going to be. So you don't know if a ciphertext that starts ABC, another one that starts with XYZ, you don't know if you don't know the relationship of the plain text, and that's kind of the whole point of ciphertext, right? So none of this works. This is using Always Encrypted without enclaves. So none of this works with anything other than equals and does not equal. Now, if we throw in secure enclaves, it changes a little bit. What we do instead is we actually do decrypt. We actually have the key is actually pulled out of, say, Key Vault, or more importantly, I should say, it's wrapped, and then we unwrap it in Key Vault. Sorry, in the enclave. We then actually perform the queries using. We actually decrypt the columns in real time in the enclave using the key, but the key never the data encryption key never leaves the enclave ever. And so, but once it's found a let's say you do a query, and you could do select star from customer where SSN, let's say you got like last 4 digits SSN is greater than 5555. It will actually do that query. So the ciphertext will go up to the enclave. It will then decrypt it in the enclave. Then it'll query over the table and return a result set. So let's just say 10 rows. But that SSN column is still encrypted. Then the client driver will decrypt it and then present it to the user. The nice thing about that is, as I sort of alluded to, you can do more queries in the enclave because we technically have access to the plain text in the enclave. The plain text never leaves the enclave, and neither does the data encryption key. Never. And again, remember, this is an isolated piece of memory. You can't reach it from SQL Server. The other really nice thing about this is that you can actually do in-place encryption or initially, let's say you got a database that's a million rows or something, and you want to encrypt like 5 columns because you want to use Always Encrypted. You could actually do the encryption in place. There's no need to sort of move the tables off somewhere and then encrypt them and then move them back or anything like that. It can all be done in place, which is super, super nice. Let's go back to our architecture diagram. So this is what we originally had with all the logging and auditing going on. Now let's just add Always Encrypted. We're going to say that some sensitive columns, we're going to use Always Encrypted. So let's say that database includes non-sensitive columns. It also includes Always Encrypted columns. We haven't sort of talked about it all, but SQL RBAC, roles and so on, and row level security, which we didn't talk about either. But these are all options for reducing access to the data that's held in SQL. And again, the client needs to have access to the Always Encrypted root keys. And again, you can also restrict access using RBAC on Key Vault. And in fact, one thing that I spend a lot of time when I'm reviewing internal threat models is I spend a lot of time understanding what the RBAC policies are on Key Vaults, because Key Vault turns a crypto problem into an authorization problem. That's what it does. So do be aware of the fact that you have to have strong RBAC controls on Key Vaults. All right, so this is kind of what our architecture looks like so far. It's beginning to look pretty good, but we'll come on to the design a bit more detail in a moment. Next is data integrity. So everything we've covered so far around crypto has really focused on mitigating disclosure of data. Now, Always Encrypted includes tampering as well, but only within the cell. That's a whole nother discussion. If at some point you wanted me to sort of dive into the gory details about how we actually do it, then more than happy to have that discussion at some point. But what about just straight up tampering? The example, we have a demo. So my colleague, Peter Van Hove, and I did a demonstration at PAS actually last year. Or he actually did the demo. I wrote the demo, he did the demo. But what it was a World Cup betting scenario. And the example we talked about was, someone betting on let's say, I don't know, Netherlands versus Belgium, which is always a grudge match, right? And let's say, you decide to bet on the Netherlands winning, and let's say Belgium won. Well, what happens if the person betting actually had a contact on the inside of the betting company and said, hey, you need to change my bet from Netherlands winning to Belgium winning, you need to do it now. And by the way, the $15,000 we're going to get, I'm going to split 50-50 with you. That's a real threat, right? In fact, there's other demos that we're working on right now. But you got other things like, healthcare information, right? I mean, that's something that's also really important, is understanding things like medicine dosage and being able to verify that the medicine being delivered is actually the correct medicine, the correct dosage. Supply chain stuff is so important, right? Because you need to make sure that whatever you receive is actually what you ordered and wasn't manipulated along the way. And so supply chain is incredibly important. And we have a technology that we have in SQL now, which even will mitigate against, let's say, naughty admins there, but will actually even mitigate against a malicious insider admin who has completely unfettered access to the environment. And that, as you probably already guessed so far, is a new feature called Ledger. Now, this is designed to mitigate tampering even by a rogue admin, someone who has absolute access to everything. It's designed to mitigate against that. Even someone who has access to cryptographic keys. It builds on top of temporal tables, but the major difference is that on a regular basis, we take SHA-256 hashes of the data that you're interested in a table that's been marked as supporting ledger. And then we store that series of hashes in storage somewhere. Now, here's the single most important point of this entire slide. It is absolutely critical that the resulting digest, which by the way is called a Merkle tree, it's actually a tree of hash values. The reason why we use that is because it's actually very fast, very efficient to search. That's the reason why we use it. It's incredibly important that that resulting set of digests, or that Merkle tree, is protected and stored in something that cannot be tampered with. Not, oh, it's got really strong RBAC controls, because a rogue admin can still go in there and change the RBAC controls, right? It's more of cannot do it, like cannot do it. And there are two major ways of doing that today. One is immutable storage, and the other one is confidential ledger. The one that's used by far the most is immutable storage. Immutable storage basically says that, and there's actually two versions of immutable storage. All it is blob store. It's blob store where you just say it's immutable storage. And there's two ways of doing it, and we recommend you use the time-based retention policy. So for example, you may have a retention policy that says 180 days. And what that means is for 180 days, you can read the data, you cannot write it, you cannot modify it, you cannot delete it. It's not that we have really strong RBAC policy around that. No, that's not the case at all. It's that the APIs are actually not there. And in fact, if you phone support and ask them to do it, they actually can't do it. It's not because policy won't allow them to do it. It's because they actually can't do it because the APIs are not there. Legal hold is basically, it's on legal hold until someone says, oh, we're not on legal hold anymore. Whereas time-based policy is time-based. And in fact, the only way you can delete an immutable storage that's on time-based policy is to delete the subscription. And I would argue that if someone can delete the subscription, then you probably got worse problems than someone being able to manipulate immutable storage. So it's highly recommend that you use the time-based locking instead. Now, if you're really interested in this and really want to learn more, and you're a real sort of nerd, then go and look at this compliance document. It's done by a third party called Cohasset. It's up on the servicetrust.microsoft.com. You need to log in to get to this and look at this document. And it's basically their security assessment of immutable storage and how it complies with various, mainly financial standards around, not being able to change data. So, for example, if you have, some sort of figures for quarterly earnings, you want to make sure that data has not been tampered with when you actually present it to the, to the appropriate shareholders. And so you can use, by the way, I don't pretend to be an expert in any of these compliance programs, but that's an area where you can actually store those documents or that raw data for that matter. So yeah, if you're a real nerd and want to sort of learn more about how it really works under the covers, there you go. Go and have a look at this document. The other really nice thing about this is you can have an independent audit. And so there are stored procedures that we have in SQL. They put like a cool thin wrapper around it in some app or something. And so long as the user has the view ledger content permission, they can go and by the way, you could have it so that they can just do that and nothing else. They can go and look at the ledger and verify that nothing has been manipulated outside a band, or it has, and then alert people accordingly. So let's take a deep breath. So using the Bing image creator, which uses OpenAI's DALL-E at the back end, let's take a deep breath in the style of Van Gogh, and here you go. So take a deep breath and let's bring this all together. So here's our design now that we've added immutable storage and we've added ledger down the bottom. We've got a new user or new role in the environment now, which is the auditor. Now, so this is kind of what our environment looks like. So I'm going to segue to something super duper quick and then come back and then wrap it up. So this is a nice segue, even though you may not even realize it at this point, is a nice segue into threat modeling. So we're huge fans of threat modeling at Microsoft. We do threat models for absolutely everything. Last year alone, in fact, not even a year, probably 10 months, I reviewed like almost 130 threat models just for the database group in Azure. And so this is what we sort of look at, like spoofing, tampering, repudiation. It's called STRIDE. It's basically a series of what an attacker is trying to achieve. So for example, let's say you have some data at rest, right? It can be tampered with. It can be viewed, and that's information disclosure. If you have a process, it can be spoofed, right? And there's all sorts of other things as well. And so different types of elements in a diagram are subject to certain kinds of threats. But that's a whole nother discussion for another day. The cool thing is that you can actually mitigate these threat types with very broad categories. So for example, you mitigate tampering with integrity controls. And that includes things like strong authorization policies or cryptographic controls. So in the case of tampering, that would be, say, hash or an HMAC or digital signature. Then if you look at information disclosure, that's mitigated with confidentiality controls, which again is authorization policy, and cryptographic controls, which is basically encryption. So if you go back to our diagram here, you'll actually see that we've talked about some of the mitigations, but they're actually under the covers, even though you may not even realize it. You're actually mitigating very specific threats. Like, how do you know this user really is a valid user? That's a spoofing threat. Well, we're going to use client authentication using AAD. Correct answer. When I connect to the SQL server, that's a spoofing threat. How do I know it's actually the correct SQL server? That's a spoofing threat. How do I know that? And the way you mitigate that is with TLS. Fantastic. When SQL Server writes to this audit log file, how does this audit log file know that the correct SQL instance is actually writing the correct data to the log file? That's another, again, a spoofing threat. And the way we mitigate that is with a managed identity. Absolutely the correct answer. And then down the bottom here, you got things like the actual ledger files, for example, and they help mitigate repudiation threats. So repudiation threats are all about going back on a transaction. There's things like repudiation of origin, repudiation of destination, repudiation of delivery. There's all sorts of things. But what's interesting there is that repudiation threats are actually quite difficult to mitigate. Certainly with these, but ledger is a fantastic way of mitigating non-repudiation scenarios because of the immutability storage, or the immutability story, I should say, on the storage account. You can actually say that, hey, after 90 days, we just detected that someone tried to change something, and it doesn't calculate it out. The ledger doesn't verify, and then you trace it back. And say, Mary tried to tamper with this bet to change it so that the Netherlands one or Belgium one, so now we can actually show that she actually changed the original wager, so that from Netherlands winning to Belgium winning. And so we can actually see that, and you can do it with a very high degree of confidence because the actual hash files are stored in immutable storage, and that's the absolute linchpin. So the other nice thing is, I sort of touched on this briefly, but with TLS, you're not just getting the server authentication, you're also getting the tampering and information disclosure threats addressed as well, which is super duper nice. All right, so some things to look at. Just so you know, like a big focus of the team I'm on is Always Encrypted, Azure Active Directory for client authentication. We're really moving heavily over into that, and Ledger. These are all incredibly important mitigations, especially when you consider assumed breach. So again, look at Always Encrypted, right? The keys are not there. Look at AAD, the credentials are not there. Look at Ledger. You can't actually delete the data. You can't change the data. You can view it, but you can't delete it. So again, in an assumed breach environment, mutable storage is a fantastic last line of defense there. Understand some of the security, core security principles like authentication, authorization. I hear people say all the time. Remember, I told you before, I'm a really pedantic when it comes to wording. Hear people say we use OAuth 2 authentication. OAuth 2 isn't authentication, it's authorization, right? So make sure you understand that. OpenID Connect, if you're using OAuth 2 environments, is authentication, but OAuth 2 is authorization. So, but understand some of those core principles as well. Understand how some of these specific, these security mitigations actually work. I mean, TLS, the server authentication aspect of TLS is so important. Yet people have, trust server certificate equals true, and they use self-signed certificates all over the place. There's no authentication going on there whatsoever. Understand threat modeling. There's plenty of resources up there. You can always go to Microsoft.com/SDL. There's lots of threat modeling resources up there. And finally, apply some of these skills that hopefully you've learned to your designs. And finally, a big thank you. There's my email address if you have any ongoing questions. And hey, go and check out the Azure Security Podcast. It's available in all the places: Spotify, Google, Apple, Amazon, and also just on the website as well if you just want to listen on the website. And with that I've got 6 minutes until the end, which is a little bit better than I thought. So can I take any questions, any comments?
Thanks, Michael. Excellent session. So far we have one question. Can we say TDS8 is usual for the connection? Is used for the connection, sorry. I said, yeah.
I'm sorry, what was the question about TDS8?
Can we say TDS8 is used for the connection?
Yeah, there's a so right now it's configured at the connection string. But in SQL Server, you can actually validate that it's actually using TDS8. There's like a little SQL query you can run that will tell you what the connection type is. Yeah. You will see a big push. TDS8 is kind of interesting, right? Because it adds this new ability, right, which is encrypt equals strict, which means that connection strings are not backward compatible, right? So if you have a TDS8 connection that says encrypt equals strict, you can't take that SQL connection string and just have it run on a SQL server that's running, say, TDS7, because it won't recognize what strict is. The other issue there is that there's a class builder, an object builder in .NET that was changed around around 5, .NET 5, I could be wrong, where the builder let you say, historically it was a Boolean, was encrypt equals true, encrypt equals false. Well, now it's an enum, right? So it's false,